All right, team, welcome to the Ravit Show. I wanted to start with good news that I was selected for the LinkedIn Creator Accelerator program. And this one's in India. So 200 creators have been selected. So thanks for all the support that you've given to the Ravit Show and to the love that you've provided for the content that we are providing. So thanks a lot once again. And also, we have a very special guest today. It's none other than Wright, who's the creator of Quine. And today we will be discussing how streaming graph makes it easy to get value from event-driven data, why you need to stop querying your data, and much more. Also, very quickly, just let us know where you're joining from, and also feel free to ask questions around streaming data, and can't wait to definitely discuss that a little about Wright. He's, like I mentioned, the creator of Quin, and has been leading software teams focused on data infrastructure and data science for 2 decades. He has served as principal engineer, director of engineering, principal investigator on DARPA funded research programs, and is currently the founder and CEO of DAT, the company supporting Quin. Ryan particularly enjoys making the philosophical ends of computer science more practical and useful. This usually involves problems related to language, meaning, and data. So can't discuss around all these stuff. So bring up the questions. Also, since we are here, what we've done is, for everyone joining us, we are giving away 1 annual subscription of 365 Data Science. And what you just need to do is type in hashtag 365 Data Science in the chat, and towards the end of the show, we'll be announcing the winners with the cool raffle that we usually do. And yeah, that's about it. Let's not make our guest wait anymore and bring Ryan up here. Hey, Ryan, welcome to the Ravit Show.
Yeah, thanks for having me. It's a pleasure to be here.
Awesome. I was just letting folks know about, that we would be discussing how streaming graph makes it easy to get value from event-driven data, and also why you should stop querying your data. Real-time event-driven data applications are forcing for us to rethink how we extract value from data and all those stuff. So can't wait to hear your thoughts around it. But why not start with your introduction, Ryan?
Yeah, absolutely. So I'm Ryan Wright, founder and CEO of that. And I created a long time ago a piece of software that we've just open sourced. So that software is called Quine. And you can see the link up at the top there, quine.io. It's the world's first streaming graph. And it's kind of sits squarely in between 2 worlds. So the world on one side of streaming data like Kafka and Flink and that kind of high volume data processing, and the world of databases and data storage on the other side, and querying that data to find out what's in there, what does it hold, where's the value, and how do I get to it. So for me personally, that journey was through a lot of technical background and a lot of technical sides of the coin. So I'm an engineer by training and background. And I've worked on data platform and data science teams really for the last several decades. So building back-end systems to process data, to take that high volume data and turn it into something meaningful, something high value that is important to the business. So leading those software teams has been my bread and butter for a long time, and we were very, very grateful and honored to be sponsored by DARPA to do a lot of core research behind the technology that we developed and just recently open source called Quine.
Nice. I think definitely you're doing great stuff in this space. And with Quine, I would love to know, how did you guys start Quine, and what was the idea behind it? Is there a co-creator with you, or was it just you when you started, and why did you build it, Ryan?
Yeah, so Quine was kind of cross between a thought experiment and a labor of love initially. So I had been leading data science and platform teams and doing a lot of the same kinds of things over and over again. So, building data pipelines, and after you build a couple data pipelines, they tend to have the same shape and are doing the same things and have a lot of the same problems. and they're really, really, really tricky. So it requires kind of taking a database and turning it inside out to be re-implemented by a team of dozens of software engineers. That becomes your data pipeline. And after you do that several times and it's just brittle and it's hard to change and it's painful to work with, you do that a few times and you have to start asking yourself, isn't there a better way? Can't we solve the problem above this, like the meta level problem that we could then, keep us from having to re-engineer this complex monstrosity every single time? And so that was some of the original motivating use case. And so I started this project just entirely on my own as initially a thought experiment. So kind of like you mentioned in the intro, like my background kind of tends in the philosophical direction. And for me, this led to questions about like the philosophy of language and how do we know things? How does knowledge work? Those questions seem to lead pretty directly into how does data mean something to a business? And how do we know what's actually in there? How do we make use of what's in there? What does it mean to have this data informing us about something? Some of those big questions turned into very practical questions to say, well, a graph is a really expressive way to represent data. We usually do it in relational tables or maybe a tree structure like a JSON, but a graph is kind of a superset above that. And it's a really useful, expressive way to think about data. And so what if we start with a graph? But the problem has always been that they're really slow and they're good for kind of toy problems. So what would it look like to build from the ground up a graph that could be fast and could be aimed at the modern data problems that are really around this high volume data world of streaming data? So not this static data where it goes and it sits there and occasionally you issue a low volume query. But how do we use a graph for high volume streaming as data moves through a backend system for a big enterprise company? So these were some of the initial questions floating around, and what really originated the creation of Quine, I guess about 7+ years ago now at this point.
Oh my, that's huge. Okay.
So the development story in the early days was long and slow and kind of on the side, and my wife would cover the kids on a weekend while I would, go do some work off in a coffee shop, and other times just have to get up early in the morning to just kind of buckle down and try to move the ball forward a little bit further and a little bit further. So the earliest days of Quine were, very much that kind of a painful exploration. And we were very fortunate that around 2015-16, I was leading a DARPA program called Transparent Computing, aimed at a cybersecurity problem, where that cybersecurity problem was really critical in the industry and unsolved. The problem was that if an advanced nation-state level attacker gets into an enterprise environment, the state of the art is you're out of luck. You can't find them. You can't stop them. There's really nothing you can do. And so DARPA was hoping to help create new techniques and technologies to discover and stop those bad actors. And the premise was, if you could take that data in about what all the computers in the enterprise are doing, if you could take all that data in and stitch it together into one big graph, then you could analyze that graph fast on the fly, and you could find what those bad guys are doing. Well, there was no technology for really doing that fast enough at the time. And so Quine was a perfect application on that program. So we were able to pull Quine onto that program, use it to solve that cybersecurity question, show some stellar results, and then just apply it more generally to cybersecurity in other ways, as well as outside of that realm, for just streaming data in general.
Okay, this is very useful information. And you mentioned about, obviously it's been close to 7 years now, maybe more than 7 years that you started Quine, and you've come a long way. And I can only understand the struggles the creators kind of go through in the initial years, and then obviously that's to bring up such a huge such a huge evolution, I can say, for not only just the data world but also for the cybersecurity world that you've you've worked in and you've actually gone after those bad guys. So that makes a lot of sense, Ryan. And that also brings me to a question, which is how has Quine evolved over years? Like how has, like, it's been, I'm sure 7 years back when you were dealing with data, it was completely different. And now when you look at data, obviously it's quite different. There are many more aspects to it. There's data governance that comes in, and there are many more things. Obviously we'll be touching base on that as well, but would love to hear about the evolution since years now.
Yeah, for Quine itself, how it's evolved, it's that's maybe a very long story or a very short story. It was kind of aimed at the same problem all along, but taking on different facets as the technology grew, as we started exploring different applications and started exploring different ways to solve particular problems using Quine. Early on, it was it was motivated by this data pipeline use case, and then to solve some hard problems like that cybersecurity problem I mentioned, you actually have to store data and combine very old data with very recent data. So to find an attacker who has infiltrated an enterprise environment like that, they've maybe done the first part of their attack months ago, and then the second part just now. And so you have to put those pieces together in order to understand what they're doing and to actually catch them and see what they've done. And so the data pipeline, data streaming approach had the other side of the coin of that look very much like a database, because we've got to store the data. But it took on a different flavor and a different shape, because with a database, your data goes and it sits there and it stays there static for someone to later on come ask a query of it. But in an enterprise environment, that data needs to be present as fast as possible, because you've got just an infinite stream of ever more data coming in after it.
Right.
And so pulling in old data and joining it together with new data, the state of the art in the industry is basically to use a time window to say that if I have to join two pieces of data together, then I have to define some arbitrary amount of time, like 30 seconds or a minute or 10 minutes. And if both parts I'm trying to join, if they arrive within that window, then I can join them together. So I hold on to an A while I wait for my B's to stream in. And when I get a B, I compare it to my A and join it. Got it. Good. But what if my B comes first? And then I'm waiting for the A's and I have to join them to the B's. And then, okay, great, we've got it. If they arrive within that time window. But there's not an infinite amount of RAM to hold on to an infinite amount of A's and B's. So at some point, you just have to let them go. And so a lot of streaming pipelines settle for the fact that if you have to join data together, if it arrives within a time window, you're okay. But if it arrives outside of that time window, your results are wrong. You just miss that. And this, the state of the art in the cybersecurity world is that attackers know this. They know that all they have to do is spread out their attack, and then you won't be able to find them. And so that dual nature of a high volume streaming system combined with a stateful storage system like a database was essential to solve a lot of these really tough problems.
Okay, this is purely amazing information that you're sharing, Ryan. So when you say obviously the attackers kind of know the ball game very well, when you talk about the times that it has to be spread out very well, it has to be done in a manner which the attackers know your game, how you're kind of defending it. So how do you tackle such problems? Is it always where you like, okay, 90% of the stuff that we do will result into something which will be positive, or you can't have a direct answer to that? How do you tackle that?
We tend to think of the challenge as being starting with a high volume stream of data, and either you know what you're looking for And the challenge is, how do I find it in that, big high volume data stream?
Yeah.
Or I don't know what I'm looking for, and I need something to tell me what I should be looking for.
Exactly.
So the first one of those, where you know what you're looking for, we built Quine for that purpose.
Okay.
Because to use Quine, you just simply say, here's a query. Here's what I'm trying to find, expressed as a database query, and in the form of what we call a standing query. So it's a query that you drop into the graph and it stays there. It lives inside the graph, and it automatically pushes itself around through the data, and it automatically finds each little incremental next match of that query. When there's a full match, the results stream out. So we built Quine like that because it's a more clearly defined problem, and it gives us other capabilities that we can build on top of. And that's where that second question comes in. So what if I don't know what I should be looking for, and I want a system to tell me what is in this data? What should I pay attention to?
True.
We actually, as part of our research, and now as one of the products offered by ThatDot, we built a system that we call novelty detection, that is built on top of Quine. So it uses the Quine streaming graph to take in a high volume of data, to build it into the kind of graph under the hood that we can analyze and measure how unusual every single piece of data is that is coming into the system. And so it gets scored in real time to say, how novel is that data? And we know immediately whether or not this new piece of data that has just streamed in off the data stream, we know immediately whether or not that is totally unusual, novel, or very typical, somewhere in the middle. We even know if it's the kind of thing that is new but normal. Like it's data that we've never seen before, and yet it's common to see new data in that corner of the data.
Very true. I think I kind of like the stuff that you mentioned about, obviously knowing your problem there. And, if you know that problem, then obviously Quine is your thing. But if not, obviously that dot is also solving your problem, where the things that you need to know, will identify that as well, and we'll work on it. So yeah, that's very cool, Ryan. Also, we have a few folks joining us. Let's quickly greet them. Aditi is here. Hey, Aditi. We have a lot of folks saying hashtag 365 data science. For those who are joining us now, just to let you guys know that we are giving away one annual subscription of 365 data science. So what you need to do is type in hashtag 365 data science, and you will enter the raffle, and towards the end of the show we'll announce the winners. Also, we have Christine joining us. Hey Christine, nice to see you. A lot of questions coming in for you as well. Ryan, one question that I can see, Manisha is saying that's so true for the creator story that you mentioned about working in the mornings and late nights, and also missing on family trips. So that's so true. And she also has a question around the users of Quine. So who are the main users of Quine.io?
Yeah, we've got users across a lot of different kinds of verticals, from cybersecurity, as we were mentioning, to fintech and financial institutions, to blockchain analysis companies, to CDNs and log processing companies. The use cases are really quite across the board, and it tends to be engineers and product folks who are really faced with that challenge of, I've got a high volume of data, and I need to turn it into a low volume of more meaningful data.
Okay.
And so stepping up that level of meaning, or kind of that level of abstraction, is kind of the typical goal. So there's a bunch of things streaming through, and I have to put them together to understand what they actually mean. And so if users have just simpler cases of, I need to count how many things stream through, then they don't need a system like Quine. But when you have to start joining data together, you have to ask questions about how to interpret this, or this collection of events spread out over time are actually an important signal for drawing a conclusion about what's happening. That conclusion is the low volume data that comes out of the system.
Okay, that's fair enough. Also, one type of question that is kind of connected is also asked by George. When we talk about the users, also the industries kind of play a very important role. So, what industries would this be a best fit for?
Yeah, so some of those verticals that I'd mentioned around around fintech and cybersecurity and things like that, we see a lot of uses for fraud detection. Fraud detection runs in a number of different ways. Sometimes it's financial fraud, sometimes it's retail fraud, things of that sort. But with the fraud case, fraud looks different in every different environment. And so the ability to customize Quine, but still have it run at scale and huge volumes of data in those different customized environments has been a really key capability for being able to solve that fraud problem in a number of different industries.
Okay, that makes a lot of sense. Nice question, George. Also, that also brings me to a very curious question that I had around Quine, was why did you keep it open source, Ryan?
So yeah, there's probably a couple answers to that. I think like my own personal answer to that question is, being an engineer, I have built all sorts of things in, just from side projects to professional work and research projects, everything else. I've built those things on top of other open source applications. And so I kind of look at this world as like this open source world as a community of contributors in a lot of different ways, where the work that I've done has built on top of that from other people. And so one way that I participate in that community is to bring my work back to that community to use in the same way. Because they can go build things that would never even occur to me, or I can't see that problem, or it's other applications that like I could help with by sharing the code, even if I'm disconnected from them physically or professionally. So on one hand, just kind of giving back to the community is just a part of what it means to be an open source user and then also a contributor. And then also, we think that makes good business sense for ThatDot. So ThatDot's the company behind Quine that supports it. And the business side of that is really aimed at helping users scale their use of Quine to huge volumes of data. And we want the open source version of Quine to be freely available for folks to go look at, to explore, to understand, to find their own applications. And we hope that a huge number of users get a lot of value from that open source application on its own, and never need to pay for support or an enterprise version or anything like that, because that's part of giving back to the community and part of the capabilities that we've built into it.
Great work that you've done, Ryan, definitely for the community, and community loves it. We've seen people, talking about Quine and the great, the great architecture that you've built for them is fantastic. So thanks for that. Also, that brings me to one also very important question that we are talking about is event-driven data. So, like, what's different about real-time event-driven applications as a class that makes current pattern for querying data poorly suited to the task? Like, what are your thoughts around it?
Yeah, it probably starts at scale, and then we can talk about querying too. But the scale side of that problem is pretty real and pretty visceral. In that if you're working with streaming data, which first of all, the motivation for streaming data is it might be obvious, but it kind of begins with this notion of why wait for an answer? Your data is coming in right now, and that data gives us what we need, at least conceptually, to get the answers we need. So why wait? Why batch it up? Why come back and do this overnight and say, we'll have an answer for you tomorrow? Maybe your buyer has that item in their shopping cart right now, and the actions that you can take can affect that right away. And so that ability to respond in real time sometimes makes a big difference for for the sales and the retail operations. Maybe it's the real-time answers to questions for cybersecurity reasons. Maybe we're trying to stop fraud before the fraudster actually gets away with the thing that's valuable. And so it's usually that the motivation for real-time streaming is because you lose a lot of value if you can't get to the answer right now. And since we have the pieces of data, we have the information about what's happening as it's flying through. If we can turn that into an answer right away, then you don't have to wait and come back and have the best response be an explanation of what the bad guy did when they stole all your money or they stole all your secret security data. You can actually stop them in their tracks before they get away with it.
Okay.
And so that streaming motivation kind of comes from just those kind of capabilities that we can actually respond and get value in real time. But the challenge there is usually this high volume of data that it's not a little trickle of, here's an event and a few minutes later, here's an event. It's a high volume. And so systems have to be able to run at scale, and they have to be able to interpret data in ways that are rich enough that you can tell a system what you're looking for and what these complex patterns are that you're looking for. So scaling streaming data is pretty tricky, but it's usually involves big microservice applications spread out over lots and lots of servers doing small little portions of the problem. When you spread it out over those microservices, like we were saying earlier, it gets really painful to understand, to make changes to those systems. There's a lot of implicit dependencies from one system on how and when the other system will have its data and what kind of answers will be available. So it gets very complex very quickly if you take the traditional approach. And so the ability to express what we want to find and what we want to do with data in ways that stitch that data together into a meaningful graph, that was kind of motivation number one for us. And then to overcome what has really become common knowledge or even a truism in the industry to this point, to overcome this notion that graphs are slow. We've had graph databases for 10, 12, 15, 20, 30 years, depending on how you count. And unfortunately, they've earned a reputation for being, nice toys that you can use for small data problems, but you'll never scale them. And so, basically every architect or every data engineer that I know kind of looks at this and says, yeah, it'd be nice if we could use a graph, but they're too slow, so we can't even consider it. Let's move on and consider other topics instead. So this is the challenge we aimed at directly with Quine, is how to make a streaming graph that can handle a really high volume of data and put those pieces together into a graph without having to kind of be crushed under its own weight and become slow. The state of the art we did during our research phase, we had tried to use every other graph system that's out there. And the target, I think, for the research was around 32,000 events per second, is what we had to support. We used every graph system available from Neo4j to Titan and Janus Graph to Tiger Graph and just everything out there, and they all have some critical challenge that limits their ability in that kind of use case. So we were able to push I think Neo4j up to about 6,000 events per second, 8,000 right in there. It required a whole lot of effort, ahead of that to prepare the data, to cache it, to get it all set up ahead of time. But we got it up to 7,000 or 8,000 events per second, I think it was. And it still wasn't enough. And even other new technologies and faster graphs like Tiger Graph, they are fast if you have a read or a write load, but the combined read and write load that a streaming system has just crushes them. So the throughput just drops to the floor. So we built Quine because we had to scale up to that 32,000 events per second. And Quine has a very different kind of architecture. It combines this graph data model with a graph computational model, built on top of an old idea from the 1970s called the actor model. Those two things combine together to be able to stream data through to give us a graph data model and a graph that computes directly in that same model. That gave us the capability to then create standing queries on top of it. The query that we drop into the graph and it propagates itself through. And those things combined let us scale this graph well past the 32,000 that we need for that research program.
Wow.
So much so that at one point a customer came to that dot and said, we're interested in Quine. Our problem begins at 250,000 events per second. So can you show us something working around that scale? So we spun up a few machines for them and showed that running at 425,000 events per second on a cluster of machines that cost $13 an hour on AWS.
Amazing. I think that's like big stuff that you've done at that dot. And with Quine, obviously the capabilities that I think you're the biggest thing that I've seen is the test and learn that you've done from not only using just Quine but also going to Neo4j or Tiger Analytics and to those places. And I think those results are definitely unreal, and the customers are super happy. So this is great information, Ryan. Definitely, we have a few questions around it as well. And since we are on the challenges bit, there's this question from Manisha, and she's asking, what are the challenges that you face during streaming graphs and working with huge data?
Yeah, good question. So the challenges that we see a lot are, they kind of begin with the graph side of that, in that sometimes graphs are new and they're kind of a foreign way to think about data. The data itself, we think about it in this progression internally at our company, and this progression that we call the kite, because it's kind of kite shaped. Where you've got a single piece of data and it's just a singular value. When you put a bunch of those together, you're working with a simple structure that's a list or a set, something pretty linear. But when you put a bunch of those together, you either start working with trees or tables. And that's typically the place where a lot of data engineers are comfortable with. So trees and tables, that's our relational databases, our document stores in MongoDB, that kind of a system. And so that structure and that framework for data is probably the most common. And so sometimes the first challenge is really just understanding, how does that same data relate to a graph? Because there's this feeling, I think, that graph data is something different, something special. It's for certain kinds of use cases. And in truth, what we discovered really clearly is that graph data is just the next extension to your relational data or your tree structured data. It's the next richer expression of it, in the same way that a tree or a table is richer than just a simple list. And so getting comfortable with the relationship between tables and trees and how they naturally lead to graph structured data, then turns around and gives you some superpowers when working with that data. This is part of how we achieve such incredible results with respect to throughput and performance, is that when data is in that graph shape, the relationships between different pieces of data are readily available to you. So you get them directly, and you don't have to do extra processing like joining multiple tables together in order to understand how two pieces of data are related. And when you have that relationship easily available to you, you can incorporate it in the streaming equation. So you can use it to resolve these queries live on the fly as data moves through.
Amazing.
And so getting a little bit comfortable with that graph data model is usually the big challenge for how to use a system like Quine and take advantage of its capabilities.
Okay, this is fantastic. A great answer to a great question. Thanks for that question. Clarifies a lot of stuff, and obviously the use cases kind of depend on the requirement. It's not on for everything that you would need the graph data. So yeah, makes a lot of sense. Also, we have this question from Moodley. He's asking, can non-standing data rejects be handled by Quine?
Non-standing data rejects. I'm not quite sure what he's referring to there.
Yeah, I think maybe if Murli kind of brings up the whole question in with more clarification, we can take that on.
Yeah, he might just in case this is what he'd mean is that the Quine works with standing queries like we mentioned, where they get dropped into the graph and automatically propagate. When that happens, results stream out to wherever you tell them to go. So they go to Kafka or Kinesis. Results can call back into the graph to update data. This question might be about, well, what if I have my graph being built from the streaming data and I have a traditional question? I just want to ask a normal query, get an answer back pretty quickly, just for a one-off case. That is supported by Quine. It's built in. Quine uses the Cypher graph query language as the way to express these both standing queries and normal queries. And so if the goal is to issue a non-standing query on the streaming data, it's done in exactly the same way. You just say, here's my Cypher query, give me an answer.
Got it. I'm sure that answers for Murli as well. And since my earlier question was more around, obviously how the patterns kind of work, but also I know for a fact Manisha kind of brought the challenges up, and that brings me to a very important question, which is around, why are traversing joins so expensive in the context of real-time use cases, and how data streaming graph solves this problem? Do you have any thoughts around that, Ryan?
Yeah. So great question. So kind of related to what we were saying a moment ago, there's this relationship between graph structured data and relational data. Where a row in a relational table is essentially equivalent to a node in a graph. A node will hold properties, just key value pairs, in the same way that a row in a relational table has different columns, or a column store, a similar structure. That relationship should help anchor some of our intuitions in that the data is the same, but it's just represented a little bit differently. So an edge in a graph connects two different nodes. The edge in a relational database is usually the result of a join between two different tables. So it relates this row from this table to that row from that table. And you get that relationship as a result of maybe following a foreign key or doing a join between different tables. The problem of using a system like that in a streaming context is that processing that join is incredibly intensive. And the more data you have, the slower it is, and the more problematic and time consuming it is to do that join. So if you're trying to resolve this question about, here's a row in my table, what are the other rows that it relates to? If you have to do a join between tables to find that answer, it's a very expensive answer. So you better make sure that you really need those results. And that's kind of the state of the art. But spending a whole lot of CPU time and computation to try to figure out, I've got tables with millions of items in it. What are the two items that are related across these tables? That has to iterate through a whole lot of things that are not the answer to your question. And so that's a whole lot of wasted CPU to get to that answer. Whereas in a graph, that edge is essentially like a pre-computed join. It's computed very cheaply, it's stored directly, and so it's immediately available for essentially no computing or no processing required. And so when that relationship is available directly, it can be used to inform how data streams. And it can be used to guide standing queries that are flowing through that graph, because they know exactly where to go next. And it can And those queries can flow at exactly the perfect moment when the data is already in memory. It doesn't have to be fetched back and forth from disk. And it can flow through the graph and just yield incredible efficiencies for results.
Okay, that's fantastic answer, and definitely that brings a very good side of why you need to have like large data as well. But yeah, you're saying something, right?
If it helps, I could even show a little demo of this.
Sure,
It's
please.
running in the
Please go
background. Let me try to share my screen here.
Yep.
And then I will flip over to this website. This is quine.io. And so anybody who'd like to can go to this website and actually even do this very same demo that we'll do here. I'm just going to click on the download link here and start downloading this, the jar file, the executable for the latest release. And Quine has baked into it something that we call recipes. Recipes up here in the top tab of the website. Recipes are really just a pre-packaged configuration for Quine that defines a certain problem space. So to say I've got a certain kind of data coming in, here's what I want to do with it and how I'll build it into a graph. Here's the standing query that I want to come out and where it goes from there. So these recipes are pre-packaged. They can be demonstrations or full applications for different kinds of use cases. I'll show off this Ethereum tag propagation one. This is a really fun one. To run a recipe is really just a matter of downloading the jar and then running it with a simple command that ends in -r and the name of a recipe. So here I've got a command line open just next to my machine here, and I'm going to run the Quine jar -r Ethereum spell it right. So that one command line just starts it up and applies everything that was defined in this recipe. And the pieces of a recipe are really just the two parts, the ingest stream and then the standing queries. There's some optional things down below for styling how nodes look and adding some convenience queries to the UI for exploring data. But the ingest streams here, this recipe sets up two of them. They're going to go connect to a server that is relaying block information about the Ethereum blockchain. So it's whatever is live and happening right now on the Ethereum blockchain. So it comes from a source that delivers blocks, and then a second source gets joined to that of the transactions that are mined in that blockchain. So each of these URLs defines a source, a streaming source of data. That data comes in and it uses this cipher query to build that data into a graph. And if we go to, since I'm just running it locally here, if we go to localhost, port 8080, then you'll see some of what is streaming in.
Oh,
so
wow.
This is the blockchain that is streaming in behind the scenes. And so these are the blocks that have been just recently validated. If I mouse over one of these blocks, you can see a bunch of its details about the gas used and the hash and the miner and all sorts of things of that sort. Wow. So this chain then continues back as far as we might want to explore. But I can click around on this graph and start to see what the whole blockchain looks like. This block was mined by that account. These are the collection of transactions in that block. This particular collection only had two, and both of these transactions didn't transfer any way. That's the Ethereum currency, but sometimes there's other reasons to issue a transaction. If we click on some of these, you can see this transaction went from that one particular account to this other account. Or we could just click on an account and say, show me your outgoing transactions. And it draws this dotted purple edge here. So we can explore the blockchain in this fashion just by clicking around and seeing what graph is built from those two streams of data about the blocks coming in and being validated. And what transactions occurred in those blocks. But so far, this is basically just like a graph database, to bring that in, to build a graph, to visualize it and look at it. But where this starts to become really fun is with the second part of the recipe. This recipe defines a standing query. That standing query has two parts. So it's the pattern we're going to look for, defined with just a cipher query, and then the output, which is what am I going to do every time there's a match. And instead of explaining the query, I'll just show this to you live of how this works behind the scenes, where the transactions in this blockchain, again, it's just whatever's live and happening right now. If I was suspicious of some of the movement of money in this account, and I thought that this account right here had maybe stolen some of their cryptocurrency, and I wanted to know who receives their stolen currency. Monitoring that on the blockchain is pretty tricky. But in Quine, in a recipe like this, it's baked into the standing query. I can come in here and just right-click that node and say, this is the one I'm suspicious of. I'm going to mark it as tainted. And when I mark it as tainted, it just sets a property on that node. And you start seeing some things flying by over here on the left side, because these are results of propagating that standing query, where we are saying that if that transaction was a part of a validated block, then anybody who this account sent money to should also have a tainted tag. So this guy has a tainted value of 1. This account over here received money from that account, and so it has a tainted value of 2. And behind the scenes, there's lots of other transactions going on. As this data moves, or as this money moves through the Ethereum blockchain. And so as data moves back and forth, as data moves through the blockchain to other accounts, that money causes other accounts to be labeled as tainted and lets us follow that movement of the money in real time as it's transferred around. And all of that is done with a right click by just simply saying that's a tainted account over here, and the standing query that watches for that tainted value on a validated transaction and moves that value through the graph automatically behind the scenes.
Oh my, yeah. I think, Brian, this is super powerful coming from Quine, and everything happening in real time is kind of, obviously I'm sure with a lot of companies in the fintech would want to learn more about this and how you're kind of tracking all the stuff. And do you have any use cases around the fintech folks that you're already working with, Brian?
Yeah, we do. So this kind of blockchain analysis is a powerful use case being applied. And graphs show up in a lot of the fraud, questions around money moving and how do you follow it, or certain kinds of transactions or attributes about those transactions being the signal of fraud, and they occur embedded in this big graph of transactions. And so fintech has been a very important space for bringing this technology to show value there. And even the novelty detection side that we talked about earlier is already live and helping folks with the auditing process. So helping to automate their financial transaction evaluations. As human auditors have to pour through this kind of categorical information about transactions, they want to find what's unusual, what stands out as being anomalous. And so these kinds of applications are really finding a lot of value in that space.
Oh, that's fantastic. And thanks for all the explanation out there. And I love the demo that you've given, because this is something obviously behind the scenes which you guys are doing. And it's so real time that you can look at each event so clearly. And very cool, Ryan. Also, we have a very interesting question from YouTube. So wanted to take this one since we are on the streaming bit and the graphs. So Ravina Ostwal is asking, how do you manage data governance while creating streaming graphs?
Yeah, great question. Data governance is a tricky subject for every enterprise, I think. Yeah, and part of where Quine fits into that picture is as part of the stream processing piece. Quine both processes data and then helps facilitate the storage of data. And that storage layer we built to be deliberately swappable and configurable. And so as data is processed through the Quine graph, typically it gets stored in a system like RocksDB or Cassandra behind the scenes. And so one of the reasons we chose this approach was, on one hand, because some of those systems are just very robust and very, very good at their job of storing that kind of data, and they're the right kind of interface for what Quine needs to store under the hood. But also they're known commodities in the enterprise world. And so that actual data storage is typically where the governance question orbits around, about how long you hold on to this, how you expire data out. And so using traditional tools lets us leverage other solutions in that space. And so folks familiar with how to manage their own particular data governance challenges, that tend to be very regional and very specific to different industries and different locations. Folks that are familiar with those kind of data governance challenges using traditional tools will find that their traditional approaches can still be applied with Quine.
Okay, that's amazing. And we also have George Ferrikin here, who says data governance rocks, since he's a very big leader in the data governance field. So he knows the importance of it. And Ryan, definitely, you know how critical this data governance plays a very important role. So thanks for that question. Ravina brings up great insights around that. Also, George has a question for you. Do you think that the demand for streaming graph is increasing?
Absolutely. So it's it's an interesting time in that streaming graph is really a new concept. It's I think the industry was kind of stuck in this place where the assuming that graphs are slow, and so they're not really an option for streaming data. And there was a response by certain kinds of use cases to say, well, let's use a graph database, applied to the streaming problem. And then there's just all sorts of limitations, like the combined read-write workload makes that really hard for any graph database to do well. So they don't. And this is where I think it's indicative of just where we are as an industry, as a society, that the need for real-time event streaming processing is everywhere. And this approach that says bring a database as your solution to that problem is the old approach that is not going to work in a modern data environment. And so I think one of the reasons we see such a big ascent in interest for the streaming graph is because the database approach is wrong. And for the first time, there's a new way to solve this problem. That's why we created Quine. That's why we open sourced it. That's why we gave it away, and just want everybody to find value in applying it to their streaming data problems.
Fair enough, and can't wait to definitely see the wonders that you would be doing with Quine and that dot. Ryan, before I ask a few questions around that dot, obviously I just wanted to remind our folks who've joined us just later and are wondering why are folks typing in hashtag 365 data science. It's because we'll be giving away one annual subscription of 365 data science towards the end of the show. You just need to type in hashtag 365 data science, and we will announce the winners towards the end of the show by a cool raffle. And I'm sure, Ryan, you'll find this very cool raffle since it has some automated stuff that it does, like the folks who are typing in hashtag 365 data science, it's collecting names, and it's like the drum roll towards the end that we would be doing.
Cool.
Awesome. And also, what's next for that dot? What's in the plans? Like, what are you planning to take? How are you planning to take it to the next level, and how is it looking right now?
Yeah, so we just recently released Quine as open source, and so we're trying to serve that open source community, help folks understand it. And so we've seen great uptake and a lot of community contributions back around recipes and applications and different kinds of use cases.
Mhm.
Where some users are publishing them back as submitted recipes, or kind of building their own recipes as their own definition of how to go use Quine. But for that dot, we're focused on supporting those users and especially the high volume use cases that lead beyond what somebody wants to tackle on their own with the open source application. And so when companies have found that they want to scale this to just the nth degree, and they want help doing that, that's where that dot comes in. And for applying it to different kinds of use cases in the fraud space, in the cybersecurity space, in the fintech space, in the blockchain analysis space, all these different kinds of things. Our team helps on that front for how to apply it to those realms, and then how to scale it to hundreds of thousands or millions of events per second, so that streaming graph can really be applied in those high volume data situations.
Amazing. Thanks for that answer, Ryan, and those details. Also, we have a comment from Murli here. He said his query was answered in a great demo that you've done. So thanks for that. It's time for just announcing our winners now. Let's do the quick drum roll here. And this is how it will actually select a winner for the annual subscription of 365 Data Science. Let's see who the winner is. And it is Ravina Ostwal. Congratulations.
Ravina.
Hey, congratulations.
Congratulations,
I'll reach out to you.
Ravina.
Yep. Great questions, great insights, Ryan. One last thing that I would like to ask you is if folks want to reach out and learn more about Quine, streaming graphs, which is the best place to reach out to you?
Well, I'd say start with quine.io, and you'll find a lot of information there, and you can download it and play with it on your own. If you have any questions, the top right corner on quine.io, you'll find a link to the Slack community. And there's other users are in there. Engineers who help create the product are also in there. And so any questions about getting started, or if you're curious about how anything works, if you want to dive into the code, there's links on GitHub, all those traditional kind of approaches. I'd point you in that direction to quine.io, and you can always follow on to that.com for any other deeper questions as well.
Sounds like a plan. Thanks a lot, Ryan, for all the insights that you've shared. Obviously, can't wait to do a 2.0 version with you and with the other teammates from that dot. You guys are creating big stuff out there, and can't wait to see that.quine.io community growing. And for those who have questions around it, feel free to check out quine.io. And you can also check out the GitHub repo there, the Slack channel, as Ryan mentioned, and have those questions coming for Ryan and team out there. Thanks a lot once again for the lovely questions asked by our audience, and congratulations to our winner, Ravina, for winning the annual subscription of 365 Data Science. Thank you again, Ryan, for visiting the Ravit Show.
Yeah, thank you, Ravit. Very fun conversation.